One of the most classical forms of automation is the loop. A loop can be defined as a structure in programming that tells the computer to repeat a certain action until a condition is met. This condition varies with the type of loop. The first loop you will learn is the for loop. First, open up a new script. Then type for I equals 1, colon 1, colon 10, display I, end. The disp function will display within the command window the value I. If we run this script, we can notice that I is displayed in each pass or iteration of the loop. I starts at 1 and goes through 10 as we defined in the first line of the for loop. Note that like our previous declaration of ranges, the step size of this loop can also be changed. For example, we can change the program to for I equals 2, colon 2, colon 20, and run the script again. Notice now that the loop displays 2, 4, 6, 8, 10, all the way to 20 in accordance to our step size of 2. This loop is called the for loop and will continue executing whatever is between the for statement and the end statement until the variable I is greater than or equal to 20. I can be changed inside the loop. To demonstrate this, we can change the program to for I equals 2, colon 2, colon 20, if I double equals 18, I equals 2 times I, display I, else display I, and finally we close the if statement with an end. Notice that this code will check to see if I is 18. If I is equal to 18, then the program does an additional multiply by 2 operation on I, and then displays the resulting 36. If we run the script, we can see now that 36 is between 16 and 20. The loop then sets I to 20 for the iteration after 18 and displays 20. Notice that although I was changed from I equals 18 to I equals 36, the loop still set I to 20 after this iteration. Unlike other languages, MATLAB for loops ignore the present value of the iterating variable, which in this case is I, and instead sets I to the specific value at the beginning of each pass through the loop. The loop will run for a preset number of iterations based on step size and max value. The for loop becomes infinitely useful for tasks involving generalized repetition. A good example of the problems easily solved by a for loop is finding Fibonacci numbers. We will do this in the next example. First, create a new script called Fibonacci. We will define the first two Fibonacci numbers 0 and 1 with fn2 equals 0 and fn1 equals 1. The fn2 variable represents the 0th Fibonacci number 0, and the fn1 variable represents the first Fibonacci number 1. Next, we will define n, the index of the Fibonacci number that we want. The nth Fibonacci number is defined as the sum of the two Fibonacci numbers before it. So, if n is 15, then the 15th Fibonacci number equals the 14th and the 13th Fibonacci numbers added together. For this example, we will find the 15th Fibonacci number with n equals 15 for I equals 2, colon 1, colon n, fn equals fn2 plus fn1, fn2 equals fn1, and fn1 equals fn. Finally, we will close the for loop with an end, and then we will display the nth Fibonacci number stored in fn. The n equals 15 line indicates the index. Following that, we start the for loop. Notice that I, which represents the index of the Fibonacci number currently being calculated within the for loop, starts at 2, since we have already defined the 0th and the first Fibonacci numbers. Notice that we are also incrementing by 1. Following this, we redefine fn using the fn equals fn2 plus fn1 line. This line sets fn equal to the sum of the previous two numbers. Then we redefine fn2 first as fn1 and fn1 as fn, which essentially prepares the sum for the next iteration. Notice that we cannot do this out of order. We need to shift the fn1 variable to fn2 before we shift Fn to Fn1. If you are curious, try reversing the lines to see what happens. The last lines, end and display Fn, indicate when to exit the loop and which variable to display, respectively. Since Fn represents the Fibonacci sum for I equals n, it is of interest to us. Try running the script. Notice that 610, the 15th Fibonacci number, is displayed. Now suppose we wanted to display every Fibonacci number before this one. Then we would simply move display Fn within the loop. Try running the script again. As you can see, this calculation could have been done tediously by hand, but it is greatly simplified and automated by the for loop. You can also see that every single variable that Fn has been assigned to is also displayed. There are a plethora of applications for the for loop, and its widespread use, as well as its useful indexing variable, makes it a popular choice for programming matrix access. We can see this in a quick modification of our program. We can store all the values assigned to Fn in variable fibs, which we will allocate with the zeros function. So fibs equals zeros, 1, n minus 1. And after display Fn, we can do fibs I minus 1 equals Fn. And finally display the fibs variable at the end of the whole script. The zeros function defines a matrix of size rows by columns filled with zeros. Note that the previous values are stored in matrix fibs using index I to specify where in fibs we want to store the values. Try running the script one last time. Notice that fibs has stored every single value that Fn has been within its matrix. There are many other usages for for loops. This is simply an exercise on the syntax of these structures, and it is likely that you will encounter many variations of these loops. However, keep in mind that while they all perform different tasks, their general format is always the same.